Daros gracias a todos por estar aquí. Me presento, soy Isaac Nebot, secretario del Congreso. Y en primer lugar tendría que estar aquí presentando a Hiroshi, mi buen amigo Tony Querol, ¿vale? Pero un inconveniente de última hora pues le ha impedido estar aquí. Y me ha pedido que por favor os exprese lo mucho que lo siente, ya que a Hiroshi, Tony e Hiroshi, pues aparte de tener una elevada relación profesional, pues han forjado una gran amistad. Y entonces pues le ha hecho más difícil todavía el no poder estar aquí, poder presentándolo. Hiroshi Nishimura es titulado por la Universidad de Hokkaido, en Japón, en Ingeniería de Recursos Naturales. En el año 1982 se unió a la empresa Hitachi Koki, actualmente Ricoh, y se involucró en el desarrollo de impresoras mecánicas, aquellas primeras impresoras que gastábamos algunos. En 1990 asciende a Data Products Corporation, actualmente Ricoh Printing Systems of America, y comienza su labor de I+D en todo lo relacionado con la tecnología inkjet. Es uno de los científicos más activos en el desarrollo de cabezales a nivel mundial, con más de 50 patentes, y además de brindar todo el soporte técnico a los usuarios. Con la charla que nos va a impartir, los retos de la inyección en los entornos industriales, vamos a tener una visión muy amplia de esta tecnología y además podremos conocer algunas de las premisas para las nuevas aplicaciones acuosas. Hiroshi, thank you very much for coming and teaching a little of your huge knowledge. So, when you want.
Well, thank you very much for introduction. I don't know what you said about me, but hopefully that was good. And I really appreciate ATC conference organizers, especially Mr. Isaac Nebot Diaz for having me here. Also, Mr. Fernando Javier Thomas at EFI, who connected me to this conference. And Mr. Jose Vicente Thomas at Kerajet. That was about 10 years ago. I had the opportunity to come over here, this region, to have some opportunity with the company. And the last but not least, thank you for the Antonio Puero Villanueva, who recommended me to speak here, my dear friend, mi amigo. So, let me speak about Ricoh inkjet technologies. And probably you already heard that I spent half of my life in Japan and the latter half of life in USA, California. And work-wise, quarter printer design and 3/4 inkjet technologies. That's me. So talking points about Ricoh, about inkjet printhead and modules, and technology for aqueous printheads, and technologies for aqueous printers. I talk about a little bit bioprinter, and lastly, Ricoh's focus in SDG area. So about Ricoh, this company founded in 1936. This was the Diazo paper company. Maybe I'm the last generation who remember this, that the blue paper that smells funny. But this is the origin of the company. And this is the Ricoh way, founding principles, 3 loves. Love your neighbor, love your country, love your work. So, under these principles, Ricoh started good old film cameras and also output device like printers. And then Ricoh developed computers, facsimiles, those are digital, and then digital combined into cameras and output printers. Today, our message is imagine change. And then Ricoh is expanding our portfolio to various output device, medical area, energy harvest, and 3D printing area. So we offer office products, services, and commercial and industrial printing, industrial products, and consumer products. If you look at our presence, we are a global company. This is Japanese company, but major office are other 3 locations, as you can see here. If you look at the number of Ricoh, this is about 14 billion euro company, 81,000 employees, rather large company, and I'm just one of them. Then sales-wise, half is coming from office printing. Maybe some of your office have Ricoh products, hopefully. And the other comes from these areas. And sales-wise, less than 50% is Japan, and then Americas, Europe, and others. That's the split. So talking about Ricoh inkjet, we have basically 3 different origins. One is printer origin, the other is printhead origin, third is the spray or airbrush type technologies that makes up our Ricoh inkjet technologies. So let me speak about the printer side first. So one printer that we offer for office is that office printer gel jet. The unique about this printer use water-based ink, but a little bit higher viscosity. We call it gel. So the pigment stays on top of the paper. So on the normal office paper, you can get a good print quality. So these are the printers. And DTG printers are known as T-shirt printers. This is also water-based printer. And these are the products that we offer. Third one is the wide format sign and graphics. Here I have 4 examples, but this is UV flatbed, not water. UV. This is water-based resin ink. And fourth one is a single pass web printers. This is very high speed single pass roll-to-roll type printers. All of them water-based ink. So next origin is the airbrush or airbrush type technologies. So we have this vehicle art printers, and this is the traditional way to decorate vehicles. You print on vinyl mostly and paste that onto the vehicle. This is the printer that uses spray gun or piezo inkjet system, then decorate directly on the side of the truck in this case. For the same technologies, this is the tire art decoration. So as you can see, tire stays here but spins, and here's the inkjet device, prints on the side of the tires. So you here you can see the example of decorated tires. Also, this technology can be used to decorate bottles, just like this. Bottle sits here, spins, and inkjet device goes up and down to make these graphics on the bottle. So the third one is print heads. So let me go over the history of this print head. The origin of this inkjet is 1978. Exxon, that oil company, started this research. Back then, Exxon thought someday oil will disappear, so they have to diversify their business. For some reason, inkjet was one of the research area. As rich as Exxon was, they spent a lot of money on the research. So you can see here some of the very fundamental technologies, strong technologies that today normal, everybody uses these technologies, but these were developed by Exxon. And then Exxon developed technologies, but they didn't know what to do with that. So Data Products, which was the largest printer company back then, purchased technologies from Exxon. So that's how inkjet technology came to the printer world. Later, Hitachi purchased Data Products, and then later Ricoh purchased some of the printing assets from Hitachi. So now we operate under Ricoh's name. Over the years, we developed many strong technologies, patent, and we licensed the technologies to other people. So we offer basically 3 different types of print heads. One is MH, metallic head, and the other is GH, gel jet head, that office desktop printer origin. And third one is TH, thin film printhead. MH printhead uses bulk printhead. Mode is piston pusher, and use stainless steel and nickel alloy as a material. So this printhead can handle high temperature ink and high viscosity ink. So that's the MH printhead. GH printhead, same bulk piezo, same piston pusher piezo, but this is plastic and cannot handle high temperature, but can handle high viscosity inks. Thin film printhead is bend mode, and everything is made on the silicone fab. So this is really highly densely populated nozzle and low temperature, low viscosity printhead. So this is GH printhead, some of the cutout and illustrations. This is MH printhead. We have a circulation model for MH printhead, and as some of you are aware, by circulating ink behind the nozzle, there are lots of benefits you can enjoy. I will talk about that later. TH head, as I said, is the fabricated on silicone fab fashion. So this is silicone wafer. many materials are deposited and then later diced, and that becomes this actuator of the printhead. So today we offer a wide range of printhead portfolio, and probably we offer widest range of printhead in this printhead companies. So I'm very much proud of it. So also I'm happy to announce a new family or new products that was released 2 days ago. Yeah, it was just announced. So let me see if I can. Yep.
Ricoh.
Thank you. So that's the new printheads that we just announced. So this is repeating, so I'm not going to talk about it. But if someone wants to evaluate, we can provide evaluation support. This is the drop watcher that we provide. So talking about support, we have 3 regions supporting. European regions are supported by UK folks. One is in Telford near Birmingham, and the sales side is in London. USA in California, that's where I am from. And in Japan, there are 2 companies, Ricoh Company and Ricoh Industry Company. They take care of Japan, China, and the other Asian countries. So talking about support, it's difficult to integrate inkjet into the machine. It appears to be easy when you look at the desktop printers from HP, Epson, Canon. It looks very simple, but when it comes to integration, it's not that easy. So we support that process by doing ink material compatibility test and waveform optimization and customer training, ink property measurement, jetability test. So I talked about printer and printhead, But what about something in between? That's module. So everybody needs to go through development when it comes to inkjet system. But can we make it easier? So we offer some of the components or module from our printers. So in this case, this is coming from desktop printer, and our customer prepare ink and structure media, fixer, controller, power supply, exterior. Then they can make their own products. In this case, like photo printing, thread coloring, label, card printing, and t-shirt printing. So by doing that, our customer can save money and time. This is a rather large-scale module effort, and the partnership with Ricoh and these companies are ongoing. So let's talk about water-based inkjet. Printhead, if I look at printhead, as I said, we have TH, thin film printhead, and GH, gel jet printhead. Those were developed for water-based ink to start with, so it's fully compatible. Metallic head is started from rather different origins, like oils, wax, UV. So, but over the years, we improved water compatibility to make it fully compatible. So this is a little busy, but showing our generation 1 MH printhead to the latest model. Over the years, the piezo type has been changed, and nozzle row, number of nozzles increased, circulation was added, and material, this is the biggest area that's changed. The original model had magnesium, aluminum, nickel, silicone, and it was assembled mechanically, screws and stuff. And piezo was exposed, and we did direct connection to the electronics. So in other words, piezo was exposed to outside. Over the years, we made progress. Today, our printhead is much more higher density, higher frequency, and compatible with different type of inks. So if I look at ink and inkjet, this is the matrix that I can think of. So these are ink parameters like contact angle, dissolved air, foaming, viscosity, surface tension, specific gravity, acoustic velocity, molecule size, boiling point, heat capacity, polarity, and biofertile. And each parameters have a bearing in binding on these items. One is priming, jet stability, drop shape, drying and curing, and material compatibility. And this is the matrix that, as far as I think. So if I apply that to water-based ink versus oil is smaller molecule, lower viscosity, surface tension is higher, boiling point is lower, viscosity lower, higher specific heat. So risk area, or somewhere that we need to pay attention, is permeation of the molecule, pressure wave oscillation, internal wetting and priming, and air bubble and drying, pigment sedimentation, and heating and managing ink temperature. So this is the molecule weight and molecule diameter, and this is water. Compared to others, it's pretty small, so it's easy to permeate. And this is the permeation ratio of various materials. This is rubber and other plastics and resins. And here comes metal. Metal has a least permeation ratio. All of our printheads has metallic barrier between ink channel and piezo and electronics. That's how we protect our printhead from water. Also, bonding. Printhead consists of a few laminate plates. So to bond these laminate, the very original adhesive was rather porous, so ink gets permeated through this layer. Today's latest bonding is much less permeation, and also we added affinity layer to connect metal and adhesives. Next one is the pressure wave cancellation. Water being low viscosity, when we apply piezo pulse to the liquid, what happens is this upper one is high viscosity, 50 centipoise liquid, and lower one is low viscosity case, 5 centipoise. And everything is same condition except viscosity. And this is the pressure inside the printhead. So this is where the inkjet, ejection happens. But after that, pressure still resides and dies down. Viscosity is a dampener. So higher viscosity, this dampens quickly. However, low viscosity, water-based ink, namely, doesn't decay quickly. So we have to do something about it. So one way to address this issue is to create drive pulse waveform to clamp this oscillation. So when we design waveform, there are a number of things we have to consider. Imaging. Is it grayscale, binary? Drop size can be varied. Software, any limitations, implement different waveforms. And system design, is it scanning, is it single pass? And throw distance, which is nozzle plate to the substrate distance. And electronics. Different electronics has different characteristics, especially amplifier to create waveform. And of course, ink. Very different inks have different properties. We have to deal with that. So to do that, we use optical drop watcher. Some of you may have seen this. This is very popular. You can see drops in the air and evaluate. Another way we do is we use laser Doppler velocimeter. And this is the device provided by MSE in California. This uses two laser beams, and the two laser beams cross here. At cross point, you would get or if something passed through this area, you get the Doppler effect. And because this is angled differently, you see different output from here. So this gives you a particle speed, not image, but the velocity speed measurement. So in this case, this is the, okay. this is the image of the drop. Usually this is the head, fastest portion, and the tail. This is the velocity of the head, this portion, and tail is usually fragmented and many particles, and you don't know how many are there, how fast are there. But this is the histogram of the particle. And so when you are suffering from misting or too many satellites on the substrate, this is the great tool to use. So example is, this is the drop at low speed, going higher speed. So usually head of the drop speed up faster, but very end of the drop doesn't change. This is the very end of the drop. So in between, there are lots of satellites there. And this LDV shows speed of the head and how many satellites here and the speed. What you're looking at here is elongation of the drop, stretching of the drop, and separation of the drop. And this is another example of for the same drop, as it travels in the air. In this case, drop merges into the single sphere. So it starts with elongated drop, becoming shorter, and becomes sphere. And this is really far from the nozzle, so a lot of aerodynamics kicks in, so it becomes more jittery. So this shows elongation, start from here, but tail, actually this is the head, and this is the tail. Tail is faster than head. So in the end, drop merges and becomes fair. So in the end, after this kind of effort, waveform makes big difference. This is before optimization, this is after the optimization. And also, not only waveform, other factors, like in this case, temperature, makes big difference. This is not optimized, this is optimized. Another issue of water-based ink is drying at the nozzle. So if you leave the print head for a few minutes, in this case 3 minutes, next time when you print, you see this delay, non-printing situation. It's not good. This happens because ink dries at the nozzle. And also, in this case, water-based white pigmented ink. White pigment is heavy, so it settles in the print head. So when you come back and start print, you see this kind of anomaly. So to understand this, what we do is another laser, but this time laser Doppler vibrometer, not velocimeter. So this looks at the vibration at the nozzle. So this is the nozzle, and this is the pressure chamber. So this is the output from LDV. So as you can see, this meniscus oscillates after the input. As I said, viscosity is a dampener. So high viscosity means this decays quickly. Low viscosity, this stays longer. So that's how we measure viscosity of the nozzle, at the nozzle, indirectly. So this is the system layout, and this is the nozzle, and this is the laser beam. And in inkjet world, it's well known that tickling / agitating works to prolong drying. It works. Tickling is you don't jet, but you apply slight pulse, so you move the meniscus up and down. It works, but it has limitations. Here's the data. So this is the viscosity at the nozzle. Just a second. Yep. This is without tickling. So viscosity at nozzle shoots up and go this way. With tickling, this red dots, viscosity stays the same, pretty much. But from here, unfortunately, it goes up, and actually it becomes worse than non-tickling. The mechanism is when we measure the viscosity inside the chamber. Let me go back. So this area. With tickling, that viscosity goes up together with meniscus area. But without tickling, that area viscosity stays. So without tickling, this liquid feeds the moisture to the meniscus. That's why this doesn't go up as much as this. So tickling works, but up to this point, no longer than that. What do we do? So here's the circulation that I talked about in the previous slide. You can circulate the ink through the printhead, so always fresh ink comes to the chamber area. So this is without circulation. Oh, by the way, this is viscosity at the nozzle. This is circulation. Without circulation, this is with circulation. It's better, but not perfect. The reason being the fresh ink goes to the chamber, but not at the meniscus. So by combining tickling and recirculation, this is the orange data. Meniscus viscosity stays consistent. So by doing that, this is without circulation, without tickling, and 1 hour later, no problem. Also white ink, for a while, no problem. So this works pretty well. So this is the circulation type printhead that has an added ink channel for circulation. Circulation has other benefits, like removing air from the printhead and temperature control by moving ink consistently. You can maintain a homogeneous ink temperature throughout the system. So there are a number of ink. This is ink delivery system companies offers circulation ink system, and also board supplier, inkjet board supplier provides tickle ready electronics. So that was printhead and ink. Now it's printers, water versus non-water. So this is the latex resin type water-based ink that we offer. So the problem of this issue is this is for sign graphics, and many of the substrate is vinyl PVC, and it doesn't ink doesn't soak into the media. So we need to dry quickly, and but we cannot really may let the ink dry at the nozzle. So problem was when we print slowly, ink stayed on the vinyl rather nicely, flat, uniformly. When we increased the speed, it started beading. So our chemists worked on that, and they worked on co-solvents for binding. They used Hansen solubility parameter to select correct co-solvents. And they developed new methods to measure binding speed to evaluate this ink, and also ingredients to reduce the skinning at the nozzle. So in the end, what we achieved was this is number of nozzle clogged after a while. This is the final ink formulation, non-clog and fast drying. Next one is high-speed web printer. This is also a water-based printer. And we've been doing this for pretty long time, a high-speed web printer. But it used to be a transactional printer, like statement and credit card statement, bank statement. When you receive it, you see it, that's porous media. So we didn't have to really worry about these things. This printer is meant for production printing, like catalogs and brochures. So media is non-porous. So problem was similar to the vinyl. It needs to dry quickly, but it has to, pigment needs to stay on there. So we developed basically 3 technologies. One is underlayer coating, chaotic coating, and also overcoat that has lubricant. This is to prevent smudging after print. When you rub it, it doesn't smear. And also the quick drying, we chose some kind of alcohol for quick drying as well as non-drying at the nozzle. So that's printing, but after print, we have to dry the water. And this is specific heat data of various materials. And water is here, 1, close to 1. It is difficult. It takes a lot of energy to dry. So that required its own development. So this is the IR, or not, radiation-based drying, and this is the wavelength. And different color have different reaction to the different wavelengths. So we had to be careful with the selection of the wavelength. And also paper and paper dust can explode if you're not careful. So this is explosion-proof construction. And I thought this is interesting that depending on the print area, energy requires to dry is different. And it's natural that large print area, a lot of water, takes lots of energy. But surprisingly, small area print also required rather large energy than medium-sized print. I wish I can explain why, but this is our finding. And so we came up with different types of drying method, basically 3: contact, radiation, and air blow. We combined all those to optimize. So this is our printer. This is inlet of the paper, printing zone, drying zone, and exit. So let me...
The engine contains an innovative new drying system. This advanced drying technology has enabled quantum improvements in print production speeds for offset coated papers. The new design using our small diameter heat rollers contribute to both higher drying capabilities as well as the suppression of cockling, which can occur during the drying process with other technologies. Thus, enabling our customers the ability to produce high quality, higher ink coverage, double-sided printing on paper weights as low as 40 GSM.
Okay. So lastly, I talk about this 3D cell printing. Let me see. We want the jet cell, and cell being easily settle in the bottom, and when that happens, we cannot jet. So we developed special print heads, inkjet device, which is open top, and with by applying certain pulse, this creates circular flow inside the print head. So this cell stays separated, and two fluids are used with cells, without cells, to create live organs. And I wish I could show the video, but if you apply like electronics pulse here, this moves. So this will be a new area that we are exploring. So the reason I mentioned this is that ceramics inks tends to be very heavily pigmented. So this circulation inside the nozzle, inside the print head, would be interesting topics. So last, Ricoh, we are very much ESG conscious company, and so we've been doing environmental initiative for last 30 years, and we are committed to innovate and ready to work with partners, other printhead companies, or consumables, or printers. So, thank you very much. Thank you for listening.